It weighs nothing less than 30 tons. 30,000 kilograms of muscle and bone and blubber, moving through cold water at depth. And right now it is spinning, rolling into tight and perfect spirals, banking through turns so sharp that scientists watching the footage couldn't explain what they were seeing. A 30-ton animal doing something that, by every rule of physics and biology, it should not be able to do. This simply shouldn't be possible. A humpback whale is not built for agility. It is built for mass, for migration, for endurance across ocean basins. It is one of the largest animals alive. And yet it was outmaneuvering fish, tight, controlled, precise, while blowing rings of bubbles to trap its prey in a net barely 5 feet across. Scientists spent years trying to figure out how. When they finally looked at the flipper, really looked, they found something that nobody expected. These were the unusual bumps. The leading edge of the flipper wasn't smooth. It was covered in a row of irregular, rounded bumps, like someone had taken a perfectly designed wing and deliberately damaged it. Every engineer who saw it assumed the same thing. They assumed this was a design flaw, but all of them were entirely wrong. And what those bumps actually do changed the trajectory of the entire wind energy industry. To understand what the whale solved, you need to understand the problem that nobody had thought to solve yet. Common wind turbines frequently stall. Every wind turbine blade ever built uses a smooth leading edge, clean, aerodynamic, continuous from root to tip. This was not a design choice anyone spent much time debating. It was inherited from aviation, where smooth wings had been the engineering standard since the Wright brothers. For over 100 years, that assumption went unchallenged. And it had a cost. When a turbine blade tilts too far into the wind, when the angle between the blade and the airflow exceeds a critical threshold, something happens. The airflow that was running smoothly across the blade surface suddenly detaches. It peels away from the blade like water sheeting off a tilted surface. And when it does, lift collapses. Then the blade simply stops working. That event is called stall. And in conventional blades, it doesn't happen gradually. It happens all at once, across the entire blade simultaneously. A sudden, violent loss of aerodynamic performance that sends a structural shock wave through the turbine. Components fatigue faster. Lifespans shorten. Maintenance costs spike. But here is the real hidden problem. The conditions that cause stall happen constantly. Low wind speeds, gusty, variable winds, turbulence, storms. All of it pushes blades into stall territory. All of it costs energy production. All of it wears the machine down faster than the design predicts. And the solution, for over a century, was to avoid stall by keeping blades out of those conditions. Not to redesign the blade, not to rethink the leading edge, to manage around the problem. That was the state of wind turbine engineering when a marine biologist walked into a gift shop and made a mistake. His name was Frank Fish. He was a professor at West Chester University in Pennsylvania, a specialist in aquatic locomotion, in how marine animals move through water. He had spent years studying dolphins, seals, penguins. He was not thinking about wind turbines. He was looking at a sculpture of a humpback whale. And then something really bothered him. The sculptor had placed bumps along the front edge of the whale's flipper. Fish, looking at it with a biologist's eye, was certain this was wrong. Bumps on the leading edge of a flipper would create drag. They would disrupt flow. Every principle of fluid dynamics he had studied said these bumps would make the flipper worse. He pointed this out to the shop owner. The shop owner told him politely that the bumps were accurate, that real humpback flippers actually have them. Frank Fish simply went back home. He decided to look it up in his files. The bumps were indeed very real, And then he spent the next decade figuring out what they were actually doing. The structures are called tubercles, rounded protrusions along the humpback's flipper edge. A typical humpback flipper carries 9 to 11 of them, decreasing in size toward the tip. They are not decorative, they are not incidental. They are load-bearing aerodynamic features that evolution has been refining for millions of years. When Fish and his collaborators finally built physical models and put them in a wind tunnel, what they measured stopped them cold. A model flipper without tubercles stalled at 12 degrees of angle of attack. It was a very sudden loss. A model flipper with tubercles stalled at 16.3 degrees. That's a 40% increase in the angle. And that alone would be truly remarkable for any engineer. But the drag numbers were harder to believe. 32% reduction in drag, 8% improvement in lift. All of this came from simple bumps, from a feature that every engineer had predicted would fail. That is exactly where things stop making sense. Because the whole foundational assumption of wing design in the textbooks since the 1900s was wrong. Or not wrong exactly, it was simply incomplete. The assumption was that smooth leading edges maintain laminar flow, and laminar flow is better than turbulence. But past a certain angle, when the blade is pushing towards stall, smooth laminar flow actually works against you. The tubercles don't maintain laminar flow, they deliberately destroy it, and replace it with something better. Fish's team published their results in May 2004 in the journal Physics of Fluids, but the engineers who read it carefully understood what they were looking at. Not a curiosity, a new principle. Within weeks, Fish filed a patent. Then he and Watts co-founded Whale Power Corporation in October 2004. Their pitch to the wind energy industry was straightforward. We can delay stall. We can reduce drag, and we can do it with geometry alone. No moving parts, no electronics, just the shape of the edge. Unsurprisingly, the wind industry was very skeptical at first, but the field testing that followed was hard to dismiss. Turbine blades with tubercles were tested in storms and ice, and even the edge of a hurricane. The results from those trials showed something very significant. A tubercle-equipped blade could generate the same power at 10 miles per hour that a conventional one generates at 17. At low wind speeds, the tubercled blade was operating in territory where others were barely functioning. Here is what is actually happening. Airflow meets the leading edge and splits cleanly over both surfaces. As the angle increases towards stall, the flow over the upper surface begins to separate and cascades at once. That is the problem, the uniformity. One catastrophic collapse everywhere simultaneously. The tubercles break that uniformity. Each bump acts like a tiny fixed vortex generator on the wing. As airflow passes over a tubercle, the bump generates a pair of counter-rotating vortices like slow-turning screws. These vortices continuously pull high-energy air down. They keep the airflow energized and glued to the blade. Between the tubercles, in the troughs, fast-moving channels of air stream down, maintaining flow. This entire system depends on one thing: the shape of a bump. Something so small it shouldn't matter. Because of that shape, different parts of the blade stall at different angles. You get a gradual slope. The blade continues to generate partial lift deep into the stall zone. It doesn't snap. It fades. Scientists believe the vortex mechanism is the primary driver. But there is still a significant debate. A Harvard team published an analysis in 2008 arguing that pressure distribution is what matters. Both explanations have experimental support. Neither fully accounts for all the data. Nobody fully understands it. It matters practically. If engineers cannot agree on the mechanism, they cannot design from first principles. This is the wall the field is currently working through. It remains an engineering mystery. The humpback does not have one fixed geometry. The bumps are largest near the shoulder and decrease to the tip. It is not a repeating pattern. It is a tuned, graduated system adapted to specific flow conditions. The tubercle geometry may be optimized differently for maneuvers versus high-speed cruising. We cannot replicate it yet. And we almost missed the whole thing. For a century, everyone looked at those bumps and saw damage. Come back to where we started. A self-driving car, banks of sensors, LiDAR arrays spinning at thousands of revolutions per minute, processors drawing over 100 watts, millions of lines of code, billions of dollars in development, decades of research from MIT, Carnegie Mellon, DARPA, and the system still fails in rain. That remains a critical problem. Now consider what the box jellyfish built. 4 independent visual systems running simultaneously. A self-stabilizing gaze mechanism requiring 0 neurons. A learning architecture distributed across 4 separate nodes. Real-time obstacle avoidance. Long-range landmark navigation. Associative memory at the size of a grape. On negligible metabolic energy, with 4,000 neurons. That is not a comparison that reflects well on us. We have much to learn. The German Research Foundation saw the implication clearly enough that in 2021, they funded a dedicated program at Kiel University, 11.5 million euros, specifically to transfer what the box jellyfish does neurologically onto silicon chips. Not to study the jellyfish, to become it. It is an entirely new approach. The lead researcher, John Bielecki, said it plainly. We want to stick them on a chip. This is the ultimate goal. What they are chasing is not a faster processor. It is a different architecture entirely. A system that learns locally, that processes vision at the sensor level, not at some distant central server. That makes decisions the way each ropalium makes decisions, immediately, efficiently, with the minimum possible overhead. The box jellyfish doesn't wait for permission from a brain. It acts. And that difference between a system that centralizes before it decides and one that decides where it perceives is the difference between a 100-watt processor and a nervous system the size of a thumbnail. If the Kiel team cracks the architecture, the first application is not a robot. It is a lens. This is a medical revolution. Medical endoscopes currently cannot reach certain anatomical structures because the cameras at their tips are too large, too heavy, and their lenses introduce too much aberration at the scales required. A grin lens of the type the box jellyfish grows, near zero spherical aberration, continuous gradient, 200 micrometers wide, would enable endoscope cameras smaller and sharper than anything currently cleared for clinical use. Surgeons could see places they currently cannot. Not with a better version of what we already have. With something we do not yet know how to make. Still, we are learning fast. The second application is in the sky. Drones navigating complex environments, urban canyons, forest interiors, disaster zones, currently require GPS, LiDAR, and onboard computing that adds weight and draws power and fails exactly when the environment gets most complicated. A vision system modeled on the box jellyfish ropalium would navigate by landmark, by Snell's window equivalence, fixed optical phenomena in the environment that the drone uses as anchors, regardless of GPS signal or maps. The way the jellyfish uses the mangrove canopy, not by processing everything, by knowing exactly what to look for and ignoring everything else. This is true focus. The third application is the one that changes the scale of everything else: distributed AI. Every large language model, every image recognition system, every autonomous vehicle brain currently deployed runs on the assumption that intelligence centralizes. Data flows to a server. The server processes. The server responds. The bottleneck is always the same. The center cannot scale as fast as the edges generate input. The box jellyfish has been running the alternative architecture for 500 million years. 4 Ropalia, 4 learning centers, no master processor, 1 coherent animal. It's a miracle of nature. If we understand how those 4 nodes reach behavioral consensus, how the ring nerve reconciles 4 independent learned experiences into a single coordinated movement, we have a template for distributed AI that does not require a center at all. Systems that learn at the edge, that do not need to phone home, that scale not by building larger servers but by adding more nodes, each one processing its own slice of the world and contributing to collective behavior. Nobody has built this yet, because nobody fully understands how the jellyfish does it. That is the question that remains genuinely open, not rhetorically open, actively, urgently open. We need the answer. How does learning in one Ropalium coordinate with learning in the other 3? Is there a consensus mechanism in the ring nerve? Does one Ropalium's experience override the others based on recency, based on confidence, based on something we don't have a name for yet? And if a predator removes one Ropalium, which happens, does the animal relearn? Do the remaining 3 already hold the memory? Is the memory distributed? Is it redundant? We do not know. This is still a mystery. Neurobiologist Gael Botton-Amio put it plainly. They have 4 of these things in their bodies. So how does that work? How is this coordinated? She published those words in 2023. They remain unanswered, still today. For the last century, the assumption underneath neuroscience and computing has been the same. Intelligence requires a center, a brain, a server, a master process, something that receives, integrates, and decides. That is our dogma. The box jellyfish never accepted that constraint. It did not evolve a brain and then optimize it. It evolved 4 independent systems and connected them just enough to move as one. It is a rebel of evolution. It got smarter not by centralizing but by specializing. Each eye does one thing. Each Ropalium handles one region. The statolith handles gaze stabilization with no neurons at all, just gravity and a crystal. Amazing. The result is a system that navigates, avoids, learns, and survives with a fraction of the neural resources that every other complex animal considers the minimum viable architecture. It is the ultimate efficiency. We built the internet on centralization. We built AI on centralization. We built every autonomous system on the assumption that intelligence needs a center. We never thought otherwise. The box jellyfish never got that memo. And it has been outperforming us, quietly, in warm, shallow lagoons, for longer than complex animals have existed on this planet. It simply exists. 24 eyes, no brain, a learning system distributed across 4 independent nodes, coordinated by a ring of nerve tissue, stabilized by a crystal that responds to gravity, wrapped in a bell the size of a grape. Incredible. The German Research Foundation is funding the effort to put it on a chip. The Naval Research Laboratory has partially replicated the lens. The neuroscientists are still arguing. The roboticists are watching and waiting. And somewhere in a warm Caribbean lagoon right now, indifferent to all of it, a box jellyfish is navigating through mangrove roots it has learned to avoid, with eyes tuned to the exact geometry of Snell's window, processing the world through 4 minds. Science is still sitting across the table from a grape-sized invertebrate, still asking how. We still have no idea how it works. In the next investigation, we look at a creature that solved a completely different class of problem, one that materials scientists have been chasing for decades, using a structure that labs cannot yet manufacture at scale. That one is next.